Okay, so in this video we're going to add on to the other theorems that we've learned, and we're going to talk about something called the Rational Root Theorem. And I'll give you the theorem itself in just a minute, but before I do that, you just need to remember for yourself, what is the difference between an integer what's a rational number and even good to consider what is a real number. So integers you might think of as whole numbers like 1, 2, 3, but integers also include the negatives, and they also include 0. A rational number is any number that can be written as a fraction of integers. So 3/2 is a rational number, sorry. But so is 2, for example, because 2 can be written as 2 over 1. And a real number is any number that say could represent a distance along a line. It doesn't have to be able to be expressed as a quotient of two integers. So for example, pi is a real number, even though it cannot be written as a fraction of integers, and the natural number e is a real number, and root 2, but they are irrational real numbers. And so you maybe remember from a long time ago you learned that there are many layers to this, but you could say that rational numbers include integers. If a number is an integer, it is also rational, but not necessarily the other way around. So for example, 3/2 is rational but not an integer. But all the things that I wrote as integers are rational numbers. And real numbers include rational numbers. So 3/2 is a real number, but not all real numbers are rational. And then so beyond those classifications you have imaginary numbers. So just recall those distinctions as we look at this theorem, the Rational Root Theorem. Okay, so this is the Rational Root Theorem. So suppose you have a polynomial with integral coefficients, so integer coefficients, and it has the root h over k, where h and k are relatively prime integers. Now you should write this down to the side. What does this mean, relatively prime? Well, it means they have no common prime factor. So in other words, what are two numbers that have no common prime factor? 2 and 3, 6 and 7, 4 and 13. In other words, they're already, if you have the numbers written as the fraction h over k, it's already reduced form. So if I had 4 over 6, that would not be relatively prime. They both share a 2 in common. You'd write the reduced fraction 2/3, and then they'd be relatively prime. So that would be a good h over k. Okay. So suppose that polynomial has the root h over k. So this rational root. Well, we know that h must be a factor of the constant term, and k must be a factor of the leading coefficient. So I have some examples that can help you see this. You may want to pause now so you can write down the whole theorem. But I do want to show you some examples of this, so that you can process what the theorem is saying. So let's have a look. What if we had this polynomial 6x cubed plus 8x squared minus 7x minus 3 equals 0. Okay, so h is a factor of the constant term. Well, that's the 3 here. So what are the factors of negative 3? Well, 1 and 3. And we can consider plus or minuses of those factors. Those are factors of the constant term. So those are candidates for H. The leading coefficient, 6, you have 1, 2, 3, 6. Those are all factors of the leading coefficient. In some form or another, you can get a combination of positives or a combination of negatives to get 6. So what does this mean? It means that we can take those numbers and then by writing all of the possible combinations of h over k, that will tell us all of the possible rational roots for this function. So just for example, okay, so I've got h over k, so these are my h's over here, the 1 and 3. So I could do 1 over 1, which would just be plus or minus 1. Those are some options. I could do 3 over 1, which is just 3. Okay, I could do 1/2, 1 over 2, and 3/2. I could do 1/3. If I wrote 3/3, then I'd be kind of redundant. That would be a number with where they have a common prime factor of 3, and in fact it's just 3 over 3 is just 1. So I wouldn't do 3/3, and I also wouldn't do 3/6 as well, because that would just be 1/2. But I could also include 1/6. So that gives me all of the possible combinations. And so what we have here, count them up, those are 12 possible rational roots. 12 possible rational roots for that function. And in fact, this is kind of cheating since I'm just telling you at the beginning. But you could check. I happen to know that one of them is a root. I know that negative 1/3 is a root. So if you checked with synthetic division, oops, not a 0 there. 6, 8, negative 7, negative 3. You will see ends up remainder 0, and so you see that negative 1/3 is a root. So the thing above could be factored down into x plus 1/3 times 6x squared plus 6x minus 9 equals 0. So let's just do another example for a moment, just so you can see how this works. How do we get these possible rational roots? So let's have that example. So let's look at f of x. Consider f of x equals, oops, not x, 4x to the 4th plus 3x squared minus 1 equals 0. Okay, possible rational roots. So our h's are going to come from the 1. Well, so we're lucky here, it's just plus or minus 1. And our k's, what are all the factors of leading coefficients? 1 and 4, 2 and 2. So 1, 2, 4. And that gives us possible rational roots h over k, so possible rational roots of 1 over 1, which is just 1, 1 over 2, and 1 over 4. So those are 6 possible rational roots. Okay, so at this point I'd like to give you, by the way, I will prove that theorem for you live, not on the video. I will prove it, but I thought it would be best to do it in person and not on these video notes. I do want to give you a few examples where you can practice finding the rational roots. Find the possible rational roots. So I want you to try these for the following polynomials. Okay. Okay, so here are the 4 practice problems for you. And so what I'd like you to do is for each of these to find the possible rational roots. And so I'm going to ask you to pause the video, and once you've done all of them, to come back and to hit play and then start watching the solutions. If you watch one solution and you find you got the first one wrong, why don't you watch that solution and then pause before you see all the other ones worked out so that you can rework your problems. Okay, the first solution, we've got a 6, so that's plus or minus 1, 2, 3, and 6, and from this coefficient just a 1. So that just gives us possible rational roots of 1 over 1, which is 1, 2, plus or minus, 3, and 6. For the second one, we have factors of 1, 2, 4, and 8 over here, and a factor of 1 over here. So that simply gives us plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. For number 3, we look at our factors from the constant term. We've got 1, 2, 3, and 6. From the leading coefficient, 1 and 2. Okay, so now there's going to be more possibilities. So 1 over 1. Oh, by the way, what I do is I first just go through all of these 4 numbers, because the leading coefficient always has a factor of 1. So I always just write those 4 numbers down, because all those 4 numbers divided by 1 just stay the same. So I'll write plus or minus 1, plus or minus 2, 3, and 6. And then I look at the other number from the leading coefficient. Okay, so there's a 2, so 1/2, 1 over 2. I don't write 2 over 2 because I've already got it. 3 over 2. 6 over 2, that would be 3, I already have it. So just those right there. Then for this last one, let's see, we got we got factors 1, 2, and 4 over here. And a factor of 1 and 3 over here. That's going to give us possible rational roots. 1, 2, 4, and then 1/3, 2/3, and 4/3. Okay, so now that we know all of those theorems, I want to put them all together to actually solve a problem. So solve all the roots of a problem. So we're going to do a 4th degree polynomial. So let's look at this. Solve 2x to the 4th plus 3x cubed minus 7x squared plus 3x minus 9 equals 0. So we want to solve this equation, and we want to do it by first finding any rational roots. Okay, this is our goal. We want to solve this. So let's start by going through what factors do we have. I've got 1, 3, and 9 from that term, and from the leading coefficient 1 and 2. So what possible rational roots? Possible rational roots. Well, 1, 3, 9, and then 1/2, 3/2, 9/2. Okay. And by the way, let's call this big polynomial p of x. Make our notation easier at some parts. Okay, so, here we have 12 possible roots to choose from. So let's start with the easiest ones first. Don't jump to the fractions. Let's try things like 1 and -1 to see if those will give us any success. And by the way, you don't need to jump to synthetic substitution for things like plugging in 1. 1 is really easy to just substitute like normal. 2 plus 3 minus 7 plus 3 minus 9. That is 5 minus 7 is 2. Plus 3 is 1. Minus 9 is minus 8. Okay, that's not equal to 0, so that means it's not a root. Remember, that is our factor theorem that we talked about last week. It has to, if you plug a number in, it has to equal 0 for it to be a root. And by the way, before we go any further, realize that this is a 4th degree polynomial, so we are looking for 4 roots. And, we really should, before we get too deep into this, before we start testing everything out, we should do Descartes' rule of signs, so that we know what how many real, positive, or negative, or imaginary we're looking at. So if you look, we've got 1 sign change here, 2, 3. So 3 sign changes of p of x. That means we've got 3 or 1 positive real roots. And if we looked at p of negative x, that'd be 2x to the 4th minus 3x cubed minus 7x squared minus 3x minus 9. In that expression, there's only 1 sign change. So there's only 1 negative real root. So just so we know what we're dealing with, and you'll see how this will help in just a minute. Okay, so we've tested p of 1. It is not equal to 0, so it's not a root. So we test p of negative 1. Plug negative 1 into that, we get 2 minus 3, we're plugging into p of x, minus 7, minus 3, minus 9. You don't even have to do all that arithmetic. You can see that's not equal to 0. So you can just move right along from that. Okay, so 1 and negative 1 don't work. So what have we learned? We've learned that those are not possible roots. So we try 3, and then we'll try negative 3. In this one, we will use the synthetic substitution or synthetic division. So we try 3. So we look what we got. Coefficients 2, 3, minus 7, 3, and minus 9. Okay, bring down the 2. Gives us 6, 9, 27, 20, 60, 63, 189, 180. Okay, so 3 is not a root. That's off our list. The remainder is not 0. So we try negative 3. 2, 3, negative 7, 3, negative 9. Okay, so we bring down the 2. Multiply by negative 3, negative 6, negative 3, 9, 2, negative 6, negative 3, 9, 0. Okay, so negative 3 is a root. So we got a root. That's great. So we've got a root. So that means we can rewrite our polynomial as x plus 3. That factor goes to the root, x equals negative 3. With this polynomial, 2x cubed minus 3x squared plus 2x minus 3. I'm getting all those numbers just from this line right here. Okay, so I have that information. Now, you might think like, okay, so what do I test next? So we've got to try and factor this thing down, right? This is our depressed equation. We want to factor that down into even smaller polynomials. So notice here, we found that negative 3 is a root. It could be another root. So there could be a double root, except for the fact that we found this by Descartes' rule of signs. There's only one negative real root. So we've got one, so we must have the only one. So that means all the other roots must be positive. So 3, we're now finished with 3 and negative 3. So we move on. it would be a good idea to test 9. But I'm going to skip that one for now. Let's go ahead and test out some of those fractions. We've already got the negative, so let's test the positive. Okay, and notice, so we're going to divide using the coefficients of our reduced equation. Okay. Bring down the 2, 1, negative 2, negative 1, 1, 1 half, negative 5 halves. So that's not a root. So not 1 half, what about 3 halves? Right, so I don't want to try negative a half because we already got all our negative roots. Okay, so 2 minus 3, 2 minus 3. Okay, so multiply. Okay, it's a root. So 3 halves is a root. So now we can write our polynomial as x plus 3 times x minus 3 halves times now this reduced equation, 2x squared plus 2. That one is actually easy to get the roots out of. You just set that equal to 0. Subtract the 2 and divide by 2 gives you negative 1. Okay, you want to solve the equation, plus or minus the square root. So x is equal to plus or minus I. And that satisfies our conjugate theorem too, because any imaginary root has to come with its conjugate. So we have plus I, so we have to have minus I. So this gives us all of the roots for the problem. So you can write your solution set like this. So now we know our roots are negative 3, 3 halves, and plus or minus I. So that's it. So that's how we combine all of these different theorems to actually get down to business and solve something like a 4th degree polynomial. Last thing I want to give you before I turn you over to the homework is if you were asked to solve a polynomial that looked like this, 1/3 x cubed plus 1/2 x squared plus 2/3 x plus 1 equals 0. You want to solve that polynomial. You want to jump into using the rational root theorem. Remember how it's stated, the polynomial with integral coefficients, or in other words, integer coefficients. This polynomial has fractional coefficients. These are not all integers. So you want to modify the problem so it is all integers. So you would then need to multiply this side by something to get rid of the 3's and 2's on the bottom. So you multiply by 6, multiply by the right side by 6 to get 2x cubed plus 3x squared plus 4x plus 6 equals 0. And then, now that you have this form, you can start going through and getting your factors and then your possible rational roots from there. So I hope that's helpful. And look forward to doing the proof in class. I look forward to working through that with you all. All right, God bless everybody.